Our first speaker today is Sreepada HEGADE from Lattice Semiconductor, where he's a senior manager. And the title of his talk is Tiny and Flexible ML with Lattice FPGA.
Thanks, Steve. Thanks for the nice introduction. And everyone, welcome to the tinyML presentation on Tiny and Flexible ML with Lattice FPGA. Right. So this is the agenda for my talk. Basically, we will review some of the flexibility requirements in the tinyML. Contrary to the belief that the flexibility required only in the neural network and operator supported, flexibility is required at every step of implementation in the tinyML. And we will look at some of those requirements and where it is required kind of thing. And then we will quickly walk through Lattice solution, how we provide flexibility at each step. And then we will discuss some of the trade-off and other things that the flexibility will provide kind of thing. Flexibility and trade-off will go hand in hand. So we will review some of those things. And then at the end, we will also review the framework that we will provide to enable the flexibility. Now, as I mentioned, the tinyML is not just about a neural network. Of course, the neural network inference is the major portion of the tinyML. And apart from that neural inference, which is at the core of the thing, engine and the flexibility of the engine and those kind of things, there are other things like, for example, most of the time it's a sensor integration and what kind of sensors your solution allows you to integrate and what kind of pre-processing you can do with your solutions when you collect the data, real-time data in the field and those kind of things. So those pre-processings are very important, data aggregation, because in the training also, we do a lot of like a data augmentation, and those data augmentation needs to be applied during the inference step also. Right, so that basically what kind of implementation we provide during the inference also plays an important role. Similarly, at the output also, like what we do with the inference result is also plays a critical role, how basically we interface with the humans or real world kind of interface, right? So, and basically that's why flexibility is a requirement at every step. So Lattice recognized this very early, and we came up with a solution stack which is very flexible. So in the stack we have like a hardware platform which basically provides different FPGA chip integrated with a lot of sensors and all those kind of. We provide a reference platforms so that user can easily implement their solution on this platform, or they can even customize for their own requirement, right? So we provide all kinds of tools and ability to do that. And the second layer is basically about the IP cores, the soft cores that are implemented on FPGA. So there are different cores that basically goes with our solution for different requirement, depending upon video, audio, and all kinds of processing that needs to happen. So we provide different kinds of IP cores, and even you can select for trade-off purpose. Right, and then on top of that, the next layer is the software tool, which is again provides one more layer of flexibility to implement the solution. And of course, the reference design toolkits and all those things what we provide. So it with the flexibility and kind of solution we provided, of course, we won a lot of industrial recognitions, basically awards. For the approach that we have taken in the early days of ML, and even today it is very relevant. Now, to give some flavor of examples of the flexibility at each of these layers in the stack. So, for example, at the hardware layer, we have different platforms or the boards and kind of thing, where even within our FPGA, we can do sensor aggregation. We can collect the data from multiple sensors, and then basically there are hardened and or the soft IPs and those kind of things in our FPGA that will help for a sensor integration and those kind of things. So many times they fail to recognize the need for this kind of sensor integration and those kind of things. They focus only on engine that does the neural network inference. So we kind of do a good trade-off in terms of resource, how much resource needs to be used for all this processing, pre-processing versus the neural network inference. Right. Similarly, like in terms of the IP cores, also we provide many of these things as a soft cores in the library. Of course, that the core of this is our engine itself is a soft core that can be modified and tuned for each of the different types of application, and depending upon the requirement, it is not hardened core. It is not limited. Even when we find a new network or something like that operator that needs to be supported, as this field is evolving, we can go and tune the neural network inference engine itself to get the best result out of it and to provide the flexibility that we are talking. Right. And similarly, there are a lot of pre-processing blocks that we provide. And as you know, FPGAs are good to implement many of these data processing in parallel. Right. So we provide the parallel path, and at high speed, we can implement many of these pre-processing and post-processing blocks. So I mentioned about the configuration engine. So we provide flexibility at different using different parameters, right? So we can even see, for example, user can do a trade-off in the configuration engine or the ML inference engine. How many computation cores I need to use? Okay, does my application requires more cores? Depending upon the network, they can choose the number of computation cores that is required for that particular application. Similarly, one of the main key factor that decides the performance is how much memory you have on chip versus how much memory you need external to that chip, right? So on-chip memory and off-chip memory. So, but at the same time, on-chip memories are also required for other things, not just for ML engine. It is also required for pre-processing and post-processing and other operations, or there may be other application that we are putting together with ML application, right? That may also need a memory kind of thing. So we can do a kind of a trade-off. For example, we have nice application like predictive maintenance and those kind of application where it is running like a background process. Whole ML is running like a background process, and there we like to reduce the number of memories required for the ML application and give it for something else, right? So more of a real-time application kind of requirement. So there are trade-offs that we need to do at that kind of thing, and we can do that trade-off with our framework and the IP itself. And short time to support the architecture and the new operation is another key feature of this whole engine, soft engine, right? Now, we do the trade-off, and the tool allows to do the trade-off in terms of, like, for example, the frame rate versus on-chip memory, right? So, okay, now if I have this much of memory, what is the kind of performance I get? Okay, the tool allows you to derive that. Basically, you can come up with different memory spec and then get the performance values to see. So, for example, I have quoted some of the different resolutions. What is the frame rate you will get for a given memory, right? So when you use 128 kilobytes of internal memory versus maybe 256 kilobytes range, right? So you can go with the different ranges and things like that. So we have, I've taken only few examples, extracted the numbers from few examples. The last one, for example, shows QVGA, which a large frame size, we can get like 48, 50 frames per second and kind of thing. We can trade off, right? So with all the thing. Another trade-off is about the DSP block, right? So this is the computation multipliers. Apart from the memory, that is another key resource for neural network inference. And here also we can do the trade-off. So for each performance target, what is the number of DSP blocks we need? Or do we need this DSP block for something else? So that again, this can be, we can compile the neural network or the inference runtime for different values of DSP. So if user gives the constraint, okay, I have only this much DSP allowed for inference, so how much performance I can achieve? That kind of trade-off can be done with this framework and the tool, right? So similarly, we can do the trade-off in terms of basically optimization, okay? So the framework allows you, okay, after the training or during the training, you can do like optimization, like channel pruning, right? So you can, if I do the channel pruning, so what will be my performance, what will be my accuracy, and how much trade-off I can do depending upon the overall system configuration and in the context, right? So the tool allows that kind of thing also. So here is the framework that we put it together basically to enable the entire flexibility into consideration. So at one end, of course, this is the traditional FPGA design tools where you can tune the neural network and generate a new engine kind of thing for every changes that you do in terms of internal memory, DSP blocks, and all those trade-off, right? And on the other hand, we have a neural network compiler. Basically, it will generate the runtime and those kind of thing. And also we provide the training framework that itself can do a lot of like a channel pruning and those kind of thing. So everything is integrated together so that they exchange the information between the tools, and so that it is more tightly integrated to achieve the trade-off, best trade-off that can be obtained. So now coming to the little bit more on the framework, how the framework works kind of thing internally, right? So we have kind of a published models in a model zoo. So the model zoo from Lattice contains the pre-trained models that are tuned for certain applications, right? So for the achieve the best performance and kind of a goal and those kind of thing. It's there is a range of models we can select from the model zoo. So then you can do using the training framework and other things we do provide, you can select the model and you can do the transfer learning. You can transfer all the weights and things like that. And then basically user can even, we provide utilities to capture the data and other things. User can label the data and they can start training and those kind of things. Of course, we don't heavily focus on data labeling and other things, though we provide certain utilities. User can plug in their utilities, or they can use the other open source tools. But the main concept is for optimization and other things, we need to have an integrated framework rather than everything kind of isolated on its own. Right. So similarly, we have a runtime compiler and other things, which basically provides a feedback loop. And we provide also, everything is web enabled, so user can do the data visualization, as well as we provide a nice dashboard, so wherein user can go and kind of monitor the performance and those kind of things. So the conclusion, basically, we are providing the flexibility, not just in terms of a neural network inference, in terms of number of what operations we can support. That is definitely a very important aspect, and our engine is tunable. But when we talk about flexibility, that's not just the one thing we should be considering. We should consider other things like sensor integration and available libraries to integrate with the ML engine and those kind of things. And finding the right trade-off is very important for the success in the tinyML. And we talked about different kind of resources that needs to achieve the trade-off, and balancing everything is a very important thing. So Lattice provides the framework, solution, reference designs, and all these things to achieve the best performance goals with a good trade-off. Right. So that's basically concludes my presentation. So.
Great, thanks, Sreepada. We have time for a question or two. If anybody would like to ask one, feel free to use the Q&A box on the right-hand side of your screen, hopefully, or feel free to unmute yourself and ask a verbal question. I'll just ask one about your model zoo. What type of applications do you have in there at the moment?
So models, we have many different networks types, and in terms of the application, let me go back to the slide. Yeah. So basically, we have focused mainly on the vision-based applications, network targeted. And we have a MobileNet and other things for like human recognition and shoulder surfing, and those kind of things are basically what we are targeting with our models, and we are focusing on video application like that.
Okay. And I know it's going to be case by case, but what are typical design times?
Oh, the overall design time? Yes,
Yeah.
it depends on the case by case, as you mentioned. But typically, if you start with the model zoo, right, it shortens it very considerably because you have a reference model that is optimized for our solution. And then particularly, you can do the transfer learning and other things, and you can incrementally train it on top of it, within weeks you should be able to retarget it to a new application and get it working. Not a problem. It's a couple of days, in fact. So
Okay. Yeah.
we have most of the IPs available for integration and things like that.
Yeah, I'm sure if people have got particular questions around a particular application, they can delve into that more in the Hangout at 1 o'clock.
Mm-hmm. Mm-hmm.
Okay. Thanks, Sreepada.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. HEGADE Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.